In this video, we continue with chapter 6.2, and we are going to see the definitions of what it means for a linear transformation to be one-to-one and onto, and we are going to find some theorems related to functions being one-to-one and onto. We are going to learn that a transformation that's both one-to-one and onto is considered to be isomorphic, and then we're going to see some examples of transformations that are one-to-one and onto, and isomorphic transformations. So a function T mapping V to W is known as one-to-one, or also known as injective, if and only if every vector in the range of T has a single unique preimage. An equivalent definition is that T is one-to-one if and only if T of U equals T of V implies that U equals V. So our first picture here shows what one-to-one looks like. So it's essentially saying each element in V maps to a unique element in W. So our second definition is that a function T mapping V to W is onto, or also known as surjective, if and only if the range of T is W, the codomain of T. So an equivalent definition is that T is onto if and only if every element of W has a pre-image in V. So you can see here, this is not one-to-one in our second diagram because two elements from V map to the same element in W. And so onto is saying that every element of W, it's full, can be pulled back to V. So if you have some elements of W that can't be pulled back to V, then it's not an onto function. So here's a couple of examples. So the first example is if our transformation maps R2 to R3, and it's defined by this function here, T of xy equals xyx. So here's sort of a picture of it. So you start with the xy plane, and then you end up with like a plane cutting through R3 because the x and the z values are now the same value. So that's why it's like a linear plane here cutting through. So that'd be one-to-one because each value maps to a unique point in R3, but it's not onto because there are plenty of z values here that are different from x that can't pull back onto that plane. So there's no preimage. And then a second example is if we've got the projection from R3 to R2. So this cylinder here is supposed to represent like a part of R3. There's no good way to draw R3. And it's defined by T of xyz equals xy. So it's like you capture 3D points and map them onto the plane, but you lose z. So this is onto because everything's going onto the plane, but it's not one-to-one because imagine the point like 1, 7, 6 and the point 1, 7, negative 12 are both getting mapped to the same point on the plane, but they're not the same point in R3. So everything maps onto the plane, but 2 points map to the same, 2 points from R3 map to the same point in R2. Okay, let's look at this example. The projection from R2 to R2 defined by T of xy equals x minus 2y in the first component and 3x minus 6y in the second component, or we can factor out the x minus 2y. So we can say this is x minus 2y times the 0.13. So it's not one-to-one because there's many different xy pairs that give the same value of x minus 2y. And it's not onto because points with y is not equal to 3x are not going to be in the range of t here. Okay, let's take a look at the next example. The transformation from Rn to Rn defined by T of V equals A multiplied by V, where A is our invertible matrix, is going to be both one-to-one and onto. So because A is invertible, that's going to help us out here. So T is one-to-one because T of U equals T of V implies A of U equals A times U equals A times V. And since A is invertible, we can pre-multiply by A inverse. So we can get this relationship, A inverse multiplied by A multiplied by vector U equals A inverse multiplied by A multiplied by vector V, or essentially vector U equals vector V. T is onto because the rank of an invertible n by n matrix, in this case matrix A, is n. So we have rank T equals n, and then by the next theorem, T is onto because its rank equals the dimension of the codomain. You could sort of think about that if the rank equals the dimension of the codomain, then everything gets mapped onto. There's no extra dimensions that aren't included. So let's take a look at theorem 6.6, and then we'll take a look at theorem 6.7 that we just cited. So theorem 6.6 is about one-to-one linear transformations. It says we're going to let T be a linear transformation from V to W. Then T is one-to-one if and only if the kernel of T equals 0. So what that's saying is that the only vector that maps to the 0 vector is the 0 vector. That makes some sense because one-to-one has to be a mapping where each vector from V has a unique vector in W. And so that's only going to work if 0 only maps to itself, because it can't be mapping more than one vector to 0. So let's take a look at our proof. If T is one-to-one, then T of V equals 0 and has only one solution, namely V equals 0. Thus, the kernel of T equals the 0 vector. All right, conversely, suppose kernel of T equals the 0 vector and T of U equals T of V. Because T is a linear transformation, then we know by the first property of linear transformations, T of U minus V equals T of U minus T of V, and that equals 0. And so U minus V has to equal 0 because U minus V is in the kernel of T. So therefore, U equals V, so T is one-to-one. And so theorem 6.7 now is about onto linear transformations. So we're going to say T is, again, a linear transformation from V to W, and W is going to be finite dimensional, and that's important. Then T is onto if and only if the rank of T equals the dimension of W. So this is what we were talking about, that every dimension of W is taken up by T. It's mapped totally onto that. So we're going to let T be linear transformation from V to W. Then we're going to go in the direction where we assume T is onto. That's our forwards direction. So if T is onto, then W is equal to the range of T. So rank of T equals the dimension of the range of T, which is the dimension of W. We're going to let the dimension of W equal n. If the rank of T equals n, then there are n linear independent vectors, T v1, T v2, all the way through T of vn in the range of T. Since the range of T is in W, the vectors T of v1, T of v2 through T of vn are linearly independent in W. Let's just say in W. So by theorem 4.12, that told us n linearly independent vectors in an n-dimensional space form a basis. Then these vectors, T of v1, T of v2 through T of vn, form a basis for W. So any vector W in the vector space, capital W, can be written as a linear combination of T of v1 through T of vn with the scalar c1 through cn multiplied through by them. And so then we know, well, that's just the same as T of C1 multiplied by V1 plus C2 multiplied by V2 added through plus Cn multiplied by Vn, which is in the range of T. So therefore, we showed that T is onto. Whew. So that second paragraph was our backwards direction of the proof. So we have an if and only if statement. Sometimes we write this with 2 arrows. Meaning, if and only if, you got to have both directions true. So when we do the proofs, we typically do the forward direction and then the backwards direction, or you can do the backwards direction and then the forwards direction, but you assume one side of the if and only if, and then show the other side must be true. Okay, now we're going to think about the situation if V and W both have the same dimension. So we're going to let T be a linear transformation from V to W, and vector spaces V and W both have dimension n. Then T is 1-to-1 if and only if it's also onto. So let's take a look at this proof. So we're going to start with the forward direction. So that means we're going to assume T is 1-to-1, and then we're going to show that that must imply that T is also onto. So if T is 1-to-1, then by theorem 6.6, we know the kernel of T is the zero vector, because only the zero vector maps to the zero vector in 1-to-1 situations. And then we know the dimension of the kernel of T is 0. So by theorem 6.5, the dimension of the range of T is n minus the dimension of the kernel. So that's just n minus 0, or n, which is the dimension of W. And so we know from theorem 6.7 that we just proved then T is an onto function or transformation. So now let's look at the backwards direction. So in the backwards direction, we assume the function is onto, and then we're going backwards to show that must mean that it's also 1-to-1. So we're assuming T is onto, and then the dimension of the range of T equals the dimension of W equals n. So by theorem 6.5 again, well, we know n minus the dimension of the range of T equals n minus n equals 0. So that's the dimension of the kernel. Well, the only way that happens is if kernel of T equals 0 vector, and then we know from theorem 6.6 that if the kernel of T is a 0 vector, that means T is 1-to-1 linear transformation. So we've shown both directions. So we've proven this relationship that when V and W both have the same dimension that we'll call n, then T is 1-to-1 if and only if it's also onto. So let's take a look at an example. We've got 4 different matrices here. They're all called matrix A, but we can think about them as A through D here. And so for all of these matrices, T is a linear transformation from V to W, represented by T of X equals AX, the matrix A multiplied by vector X. And we're going to find the rank and nullity of T and determine whether T is 1-to-1 or onto. It could also be both. And notice we made life easy by putting all these matrices in row echelon form. So let's take a look at the first matrix with the lowercase a here. So our first thing is to look at the number of rows. That's the dimension of the codomain. So this first matrix is a 3x3 matrix. So the dimension of the codomain is 3 and the dimension of the domain is 3. The rank is the number of pivots. So we've got 3 pivots here. We've got 3 columns where we've got 1s as the leading values and 0s everywhere underneath. So those are our pivot columns. And so that must mean then, well, rank is 3 and the dimension of the domain is 3. So 3 minus 3 is 0. So that means the dimension of the kernel is 0. So that means it's 1-to-1. Because our dimension of the domain equals our dimension of our rank. And then it's onto if the dimension of the codomain, the rows, equals the rank also. So since both of those are true, this is yes. So notice also this first matrix is a square matrix, and it had that nice reduced row echelon form. All right, let's take a look at the next matrix. That's a 3x2 matrix. So we know right away it's not going to be 1-to-1 and onto. So the number of rows is the dimension of the codomain. So that's a 3. There are 2 columns. So that's the domain. So this would map from R2 to R3. And so then the number of pivots is 2 here. And the dimension of the kernel is n minus r, which is 0. So because n and r are equal, this is 1-to-1, but it's not onto. And that makes sense because we don't have a square matrix here. So you can see that we're not going to take up all of R3 when we map from R2 to R3 here. All right, matrix for part C is a 2x3 matrix. You can imagine we're going to see some kind of opposite results here. So the dimension of the codomain, the number of rows is 2. The number of columns is 3. So the dimension of the domain is 3. And the rank is the number of pivots. So we've got 2 pivots here. And then the dimension of the kernel is n minus r. So 3 minus 2 is 1 here. So the null space of T is 1. And you can kind of see that from this column right here. The column that would be associated with the free variable. So we would put, T instead of x3 here. And then this is not 1-to-1 since the dimensions of the domain is 3 and the rank is 2. And then this is onto though, because the dimension of the codomain is 2 and the rank is 2. Okay, let's take a look at D. Now notice D is also a 3x3 matrix. But notice the last row of D is all zeros here. So D has 3 rows and 3 columns. So M and N are both 3. It maps from R3 to R3. The dimension of the rank, though, the dimension of the range, the rank, is only 2 because there's only 2 pivot columns here, meaning the dimension of the kernel is 1. And so it's not 1-to-1 because the number of columns is not equal to rank. And it's not onto because the number of rows or the dimension of the codomain also does not equal the rank. So you could imagine if you were multiplying here, you would lose a whole dimension here, right? You just get zeros. So it makes sense that it's not onto, and you can see it's also not 1-to-1. All right, so let's talk about what is an isomorphism. So a linear transformation that is both 1-to-1 and onto is what we call an isomorphism. And then if V and W are vector spaces such that there exists an isomorphism from V to W, then V and W are said to be isomorphic to each other. So we say the transformation that's 1-to-1 and onto, that's the isomorphism. And then if there's an isomorphism between V and W, then we say they're isomorphic to one another. So Theorem 6.9 says 2 finite dimensional vector spaces V and W are isomorphic if and only if they are the same dimension. And so that's why they have to be finite dimension, because try to imagine mapping something of infinite dimension onto something of infinite dimension. I'll let you think about that part. So since this is an if and only if statement, we are gonna do the forward directions of the proof first, and then we'll do the backward direction. So the forward direction is to assume that V and W are isomorphic. So we are going to assume V is isomorphic to W and V has dimension n. So we're going to try to show that W must also have dimension n. All right, so since V is isomorphic to W, there exists a linear transformation, T mapping V onto W that's 1-to-1 and onto. And so because T is 1-to-1, then the dimension of the kernel of T is 0. So the dimension of the range of T is going to be the dimension of the domain of T minus the dimension of the kernel of T. Well, that's just n minus 0 or n. And so moreover, because T is onto, the dimension of W is the dimension of the range of T is n. And so V and W are the same dimension. So we're making use here of theorem 6.6 and 6.7 that we proved earlier. So now we have to go the other direction. Now we have to assume that V and W are the same dimension. And then we have to show that they are isomorphic to each other. And so this is the backwards direction. Sorry, the font's a little small for me to squeeze everything in here. So now we're going to assume V and W both have dimension n. And then we're going to let V1 through Vn be a basis for V, and W1 through Wn be a basis for W. Then an arbitrary vector V in vector space capital V can be written uniquely as a linear combination of scalars C1 through Cn multiplied by vectors V1 through Vn and then added up. So then we can define the linear transformation T mapping V to W by T of V equals C1 W1 plus C2 W2 plus and so on until plus Cn multiplied by Wn, where the C's are scalars and the W's are the basis vectors for W. Then we can show that T is 1 to 1, because if T of V is 0, then C1 multiplied by W1 plus C2 multiplied by W2 added through plus Cn multiplied by Wn equals 0. And since the basis W1 to Wn is linearly independent, it's got to be that all those scalars are zeros. So therefore, then, if those scalars are zeros, then V is also a linear combination of the same scalars multiplied by the basis for V. So V equals 0 V1 plus 0 V2 added through 0 Vn is 0. So the kernel of T is 0. And so by theorem 6.6, then T is 1 to 1. And then we can show T is onto. So since T of V1 equals W1, T of V2 equals W2 through T of Vn equals Wn, then the basis W1 through Wn is contained in the range of T, which is contained in W. We saw that at the very beginning of the video. So therefore, N is less than or equal to the rank of T is less than or equal to the dimension of W, but the dimension of W is N. So these are all equal to N. So rank of T equals N, and by that theorem 6.7, T is onto. Okay, so down here at the bottom in this slide, I squeezed in some examples of isomorphic vector spaces. So these are all isomorphic to each other, meaning you could map from any one of these onto the other. These are all 4 dimensions. So R4, which is what we call 4 space. So these all have n equals 4. You could map to all 4x1 matrices, right? Because you could have 4x1 matrices where they have any of those real numbers in the spots. You could also map to the 2x2 matrices, right? So imagine this is just saying A, B, C, D could map over to A, B, C, D, right? The position doesn't matter. It would still be 1 to 1 and onto. P3 is a space of all polynomials of degree 3 or less. And so think about that. A polynomial of degree 3 or less has this form: A0 plus A1x plus A2x squared plus A3x to the 3rd power. So there's 4 terms there. So you see how those coefficients could map back to R4, and you can certainly have 0 coefficients in P3 because these are polynomials of degree 3 or less. So if like A2 and A3 are 0, then you have just a 1st degree polynomial. And so that's okay because these are not just polynomials of degree 3, they're degree 3 or less. And then you could have the vector space that is x1, x2, x3, x4, and 0, where each x is a real number. So you could have a subspace of R5. So just like how a plane is a subspace of R3, you could have, we can't really picture it because we're in R4 and R5, but you could have a subspace of R5 with 0 in the last entry there. All right, so in the next part of chapter 6, which we'll study next week, you'll look at how we can apply these linear transformations.